Solving quadratic inequalities is like solving quadratic equations. So if this was x squared plus 9 equals 0, or not 0, 25, if it was an equals sign, could you solve it? Yes. You'd move the 9 over. You'd square root both sides, not forget the plus or minus, and you'd get x equals plus or minus 4. That tells us where they're equal. We want to find out where is it less than or equal to 25. So right now, I would like you to plug in a value for x and tell me if it works or doesn't work for being less than or equal to 25. You have like, well, shaded part of the graph is when it was with a y. This is one where you had the number line with the true and falses. I don't know if that, okay? And if you tried 4, what happens? It equals 25. Can you find another number other than, because negative 4 and 4 is going to be where it's equal. We need to find out, are there other values that work? If you tried 0, it works? Is 9 less than or equal to 25? Yes. Oh. Okay. So if you try 0, it works. What we did in grade 11 is after finding out where they were equal, you put the values that were equal on a number line. Do you remember drawing circles at these values and either shading them in or leaving them open? We would shade these ones in to indicate that it could equal 4 because we have a less than or equal sign. And then after that, you did test values. We just tried 0. 0's in this middle section, and it worked. So we can say that the entire middle section is true. If we try something less than negative 4, like negative 5, negative 5 squared is 25, plus 9 is 34, is not less than or equal to 25. This section is false. And similarly, if you tried a number like 10, it wouldn't work either. What we're, in a sense, doing, okay, I could have moved this 25 over at the beginning. Would you agree that this equation is the same as that equation? Do you remember the rules for inequalities? When do you flip the sign of an inequality in an equation? When you multiply or divide by a negative number? Okay. So maybe you want to make a note. If you've forgotten that inequality rule. Inequality rules. You flip an inequality if you multiply or divide by a negative. So subtracting 25 on both sides didn't change the inequality. But if I divided both sides by negative 1, I'd have to flip the inequality. Now, with this equation, x squared minus 16 less than 0, if you graphed x squared minus 16, would you agree that'd be a parabola that's moved down 16 units? And it happens to have x-intercepts at negative 4 and 4. What we're trying to do here, when we graph this, we're graphing y equals x squared minus 16. And if we're trying to solve where is x squared minus 16 less than 0, graphically, that's really looking at where is y less than or equal to 0. Can you see from the graph that that's only true here, between negative 4 and 4? It's not true when x is less than negative 4. It's not true when x is bigger than positive 4. So we can see it graphically, but we can also test it with the number line. In fact, the number line is basically just this part of your graph. Here's 4, here's negative 4, there's your number line. And our test value is saying, does it work in this section? The yellow section is yes. That's where it's less than 0. So we put a true there. And it's going to be true for everything in between there because our function is continuous and joined all the way through. We finally would write our solution as an interval from -4 to 4. Square brackets because the values are included. Or you could write this in set notation that x is between -4 and 4. So similarly in the second example, which I'll do in green here, you can set it equal to 0. This one we can factor. And we find out that it's equal to 0 at -3 and 2. If you draw your number line, include -3 and 2. Now we want to find out when is it bigger than 0. So if you draw circles on here, they're going to be open circles because those values cannot be included. -3 and 2 are when it's equal to 0, and we need it to be bigger than 0. What happens when you plug in 0? 0 plus 0 minus 6, is that bigger than 0? No. This section will be false. If you plug in a value larger than 2, like 3, 9 plus 3 is 12, minus 6 is 6. Is that bigger than 0? Yes. And same thing will happen if you plug in something less than -3. Again, if you want to think about this graphically, we just figured out that this graph, if I graphed y equals x squared plus x minus 6, by making it equal to 0, I just figured out the x-intercepts are at 2 and -3. When you look at this parabola, does it open up or does it open down? It opens up. If we're trying to find out where x squared plus x minus 6 is bigger than 0, we're trying to find out where are the y values, because y is equal to x squared plus x minus 6. Where are the y values bigger than 0? On my graph, can you see that it could be highlighted here and here, but not in between? The same results that we got from testing values and getting it true, false, and true. So in this example, we would write our solution is in two areas. In interval notation, we would say from -infinity to -3 round bracket because it's not included, or from 2 to infinity. In set notation, we would say x is less than -3 or x is bigger than 2. How is this related to what we're going to do? Well, we're going to look at composition of functions. Right? Composition of functions was that f of g of x where you do one function first and then you do the other function. And a very typical situation is where you have one function inside of another function. Okay? I am going to skip the graphing here. And we're going to look at the explicit equation for f of g of x. And we're going to look at the domain and range of this function. So f of g of x, what does it look like? Well, we do g of x first. What does g of x do? It says whatever you plug in gets squared and you minus 1. So if you plugged in 3, 3 would get squared and you'd minus 1. If you plug in x, x would get squared, and you would minus 1. Then f of x. F of x says whatever you do, whatever you put in, do 3 minus that number, and then take the square root. So if you put in a 1, you would do 3 minus 1 and then take a square root. If you put in an x, you would do 3 minus x and then take a square root. If you put in an x squared minus 1, you would do 3 minus x squared minus 1, 3 minus, and since you're plugging in more than one thing, make sure you put it in brackets because that negative in front is going to be important in this situation. You take 3 minus that and then you take the square root. Well, what does this mean? This means that we have 3 minus x squared plus 1. Or, if I simplify my like terms, I've got the square root of minus x squared plus 4. And all of a sudden, a whole bunch of units are starting to come together and ideas from grade 11. Because if we want to find the domain of this, we have to know something about square roots. Can you take the square root of any number? No, we can't take the square root of a negative number. Can you take the square root of 0? Yes. So what does that tell us? It tells us to find the domain, the inside, the negative x squared plus 4 has to be bigger than or equal to 0. If it's less than or equal to 0, what's going to happen? You can't take the square root of a negative. If it's just less than 0, you can't take the square root of a negative. So now, how do we solve this? Well, that's that grade 11 concept. I need to make it equal to 0, move my x squared over, square root both sides, and I get x is equal to plus or minus 2. Draw my number line and use some test values. What happens if you plug in 0? Is it true? 0 plus 4 bigger than or equal to 0? Yes. That middle section will be true. What if you plug in something less than negative 2, like negative 3? Careful here. A negative 3 squared is positive 9 times by a negative makes negative 9 plus 4 is negative 5. Is that bigger than or equal to 0? No. Plug in a number bigger than 2, like 4. Remember, this squared is just affecting the x. If I plug in 4, order of operations, 4 squared, 16, times by a negative, negative 16 plus 4, negative 12. Is that bigger than or equal to 0? No, false. Again, you could think of this graphically. Can you see this parabola that opens down? What are we looking for? We're looking for where are the y values bigger than 0. They occur between negative 2 and 2. So our domain is between negative 2 and 2. How do you graph square root graphs? This was chapter 2. It's a good review. You've got an exam coming up. This is on your exam. Whoops. Easy. Got to go through that point. There's our parabola going down. Do you agree that that's negative x squared plus 4? Transformations unit, the negative would flip it down. The plus 4 shifts it up 4 units. Transformations now seem like a pretty easy unit. We've done it enough times during the year. Okay? Not sure. How do we do a square root of any graph? You go to your graph. First thing you do is label the points where it's 0 and 1. Those points don't change. Then do any other points that are easy. How easy is it to do the square root of 4? It's 2. When the blue graph is between, the y values of the blue graph are between 0 and 1, your graph has to be slightly above. Remember that? And where the y values are bigger than 1, your graph is below. There's the picture of the graph of the square root of negative x squared plus 4. Review of chapter 2. The green graph the blue graph was negative x squared plus 4. The green graph is how to graph the square root of any graph from chapter 2. That was a test you just wrote. Okay? So a bunch of review. This section is going to be doing domain and range and restrictions on composite functions when you put functions together. So the new unit is looking at this first part, f of g of x, and then looking at domains and ranges. Usually the domain and range can be done by finding the explicit equation of the composition of the functions and then looking at that explicit equation. But we also have to be careful because we have to look at the domain and ranges all the way through to make sure there's no other restrictions. So let's go to example 1, which is a little bit easier than what we did to start. Use the functions f of x equals x plus 1 and g of x equals 4 minus x squared. State the domain and range of each function. So first of all, I'm going to put that one in green, this one in blue. Can you see with the green one that it's a line with a slope of 1? Domain is everything. Range is everything. Can you see with the blue one, and maybe you want to rewrite it like this so it fits more with your transformations, that it's a parabola being flipped down and shifted up 4 units. It also will have a domain of everything, but its range will be y is less than or equal to 4. Now we want to do the composition of these functions, f of g of x and f of x, and then state the domain and range of those composite functions. So what we're going to do, okay, we're going to find the explicit equations first. F of g of x, well, we do the inside function first, always on a composition of functions. And so g of x is the inside function. What happens in g of x? Whatever you plug into the function g of x, you square it and subtract it from 4. So if I plug in x, I square x, then I subtract it from 4. Basically, when you're plugging in x, it's the easiest thing, right? Because you just have to rewrite the equation. And now for f, this is where it gets a little bit tricky, because f says whatever you plug in, add 1 to it. So if I plug in 4 minus x squared, I'm going to have to take 4 minus x squared and add 1 to it. That's the function f of x. Whatever you have inside, you add 1 to it. Now this can be simplified, and we will get negative x squared plus 5. Once we have this explicit equation, we can find the domain and range. What's the domain of this new function? It's everything. What's the range of the new function? Well, it's a parabola that's been flipped upside down and moved up 5 units. So y is less than or equal to 5. I shouldn't have rotated it, I guess. There we go. Now let's see if we can move it. There we go. Part B, we want to do f of x. Okay? So in part B, we would do the inside function first, which is f of x. If you plug in an x, the function f of x is whatever you plug in, add 1. So it'll just be x plus 1. And then we do that back into the function f again. The function f says whatever you plug in, which is x plus 1, add 1 to it. What do we get? X plus 2. What kind of equation is this? What kind of graph is this? This is a line. Its domain is everything. Its range is everything. Again, this is the explicit equation. And so we can find the new domain and the new range once we found the explicit equation. We can also easily graph both the new composite functions. It's going to be the easiest way to graph a composite function if we find the explicit equation. Negative x squared plus 5 is easy to graph because it's been flipped down and moved up 5. Why would I lose marks on this one? I have no x-intercepts labeled. I need at least 2 points when I sketch a graph. So this is going to be root 5 comma 0 and negative root 5 comma 0. Could have labeled another point 1 comma 4. So we need more than just a single point. We need enough so that whatever scale we have on our x-axis is indicated as well as our scale on our y-axis. Same thing for the second graph. X plus 2 would be really easy to graph. We're going to have a y-intercept at 2, an x-intercept at negative 2. It's a straight line with a slope of 1. And we have our graph. Okay, questions for practice. Just number 4.